Jim, you want to go ahead? Thank you.
I don't think there is any other business, so.
I've been fascinated for a couple of months about this little Pixie transceiver. And so this is what it looks like if you buy one. I got this off of eBay, and this is the first one I got. I put this one together myself. That's why I got the second one, is because this one doesn't work too well anymore. It worked actually for a couple of days, and then I kind of got creative with the power supply, and it doesn't work anymore. So I'm going to pass this around just so you can see what it looks like on the inside. I thought I'd start out with what it looks like connected. You got to have an antenna, so they stick a BNC on here that you can kind of connect to a PLC if you're 259 if you're up for it. It's got a power source that's got one of these little plugs, and it can be, is it negative inside or positive inside? Well, it turns out it doesn't matter because they put a software bridge in here. We'll go through that. You've got to put one connector in here for your key, and another connector in here for your earphone. Once you do all that, you got yourself a transceiver. Okay, so I thought I'd just pass that around in case anybody would like to take a look at that. So the question I had is, if you go back to as old as some of us are, you remember the All-American 5 radio with, it plugs straight into the AC. So you needed 5 tubes to listen to a receiver. Then the Japanese came in with the Japanese 6, and they needed 6 transistors to make a receiver. Well, how can they do this one with 2 transistors? So somebody's cheating somewhere, or shall we say, reinterpreting the statistics. So I got really interested in this just to learn. I'm learning as I go, and if I say something stupid, please correct me, because I'd love to learn from all of you. I got this presentation from the Newport County Radio Club in Rhode Island. I had looked all over the web for something I could understand, and these people did such a beautiful job. I am plagiarizing everything they did. They did the good work, and I'm merely the humble messenger. So my transmission code speed is not quite fast enough. So if I go over 18 minutes, feel free to leave. But this is their description of how this particular unit works. Let's go on to the next slide. They start from reasonably the beginning. So I thought it was pretty good to just follow what they did. So they claim you need an amplifier, which kind of looks like that if it's an op amp or something like that. You need something that wiggles, keeps itself going, and you need something that is, this is usually linear, this is very non-linear. So you need linear amplifiers and non-linear amplifiers and something that wiggles. And now you got yourself a radio. Okay, let's keep going here. Their definition of an amplifier is something that takes a signal in and usually makes it bigger. It's usually a lot easier to make it smaller, so you're usually kind of interested in making it bigger. They can have an audio or radio frequency one, and you can have power, or you can just focus on the actual voltage of the signal and not worry about how much power it gets. That's their summary of amplifiers. Okay, let's go on to the next one here. This I thought was kind of interesting. If you look at a speaker hooked up to an amplifier to a big boom box, and we've all done that, you get too close to the boom box and you get this, oh my gosh, I'm going to get back here. Okay. So you're going to get some sort of feedback in there. Next slide. And so now you're getting a bunch of frequencies over here moved back into the speaker and amplified again. So you're saying, hey, that sounds pretty good. That's kind of like an oscillator, except you're getting a whole bunch of frequencies. So how do you get that down to something pristine? Next slide. How do you make an oscillator? Okay, next slide. What you do is you put a filter in there to get rid of all the frequencies you don't want, and now you're getting something pretty pure. My humble background is in a lot of, I don't call it mathematics, I call it arithmetic, but it turns out it's impossible to get a pure frequency. Okay, there's always some wiggle on the end due to the very fact that you started it or you stopped it. So you do the best you can to get a pure frequency out. They're proposing or pushing the crystal oscillator, and the crystal oscillator, if you look at the frequency response, is about as peaked as you can possibly get. So that sounds like a really good idea. Let's go on to the next one, the quartz crystal oscillator. This is a equivalent circuit of a quartz crystal oscillator. The series inductance is usually in the millihenries. The capacitance blows my mind. I'm used to picofarads when you're, what's a puff? It's your finger right there, right? That's about a puff. And anything below that is very hard to get because just the wires themselves will give you that. This ain't no puff. This is a femtofarad. Go 1,000 times lower than that, okay? So that's a very, very small capacitor. The resistance is usually around 10 ohms. The parallel capacitance is usually like picofarads. But you start looking at the reactive resonance divided by the resistance resonance, which is usually called the Q of the soil, how long it's going to keep wiggling, oscillating before it decays away. This is like 1,000 times better than any sort of other circuits you get. And dummy like me tried to improve this thing. Again, everything I did to it made it worse. And I tried to change the tank, and you'll see. There's a really good reason to use that. Okay, let's go on to the next one. Next slide. Oh, there we go. So that was amplifiers and oscillators. What they're talking about is mixers here. And what they're trying to say here is that there's two types of mixers. There's linear mixers and there's nonlinear mixers. And usually when we're trying to build an amplifier, we're trying to focus on the linear side where, you double and you get double whatever you get up there. When you're trying to do frequency mixing, it's completely the opposite. You want the most nonlinear thing you can possibly, thank you. The most nonlinear thing you can possibly get. And so that's what we're going to look at when we go a little bit further on. So in a mixer operation, what you want to do is take one frequency in, take another frequency, and do something besides get the same two frequencies out. And if you've got a linear device, let's say a resistor and a resistor with a bunch of capacitors on it, you're not going to get mixing. Okay, it actually, when you go to do the mixing, it's kind of, you got to work at it. Okay, so what you want to do on a mixture is get the sum, the difference, and the original two frequencies together. Okay, so I think on the next slide they go through a particular example of this. This is going to be a 40-meter transceiver, and it's right down just off the tech band, right into the amateur extra band on the 40 meters. So it's like I'm a tech, so I can't quite get there. But my son is going to be visiting next month, and he's an extra, so we can go have fun when he gets it. This is an example of taking 7 megahertz in and taking 7 megahertz plus a kilohertz. Okay, you put them in, and you get the sum, you get the difference, and you get the two original ones. Okay. So just to put a fine point to this, if I could bother you to go into the other presentation, what I did was I wanted to actually do this. There we go. And so what I did was I have this computational package called Mathematica, which does all the work for you, and all you have to do is sit there and ask it to do something. So what I did was I took one frequency at 25 kilohertz and one frequency at, sorry, not kilohertz, 25 hertz, just to plot something. And then one at 15 hertz, and I just add them together. Once I added them together, then I just discretized that, put it into something called a Fourier transform, and plotted it out. And what do you get? You get a frequency here. This is the frequency domain. It's a little off by the 0 versus 1, but roughly it's giving you 15 hertz and 25 hertz. So I said, well, that worked pretty well. So why don't I just multiply it? How do you multiply them mathematically? You put the frequency in, you put an equal sign. Great. So here is what you can see that trace, that one right there looks a little different than the one above it, because it's a little more complicated. This is the one above it there. There we go. And you can see that the product of the two, there's more stuff there. Okay. Well, what is that more stuff? When you look at the frequency domain, you get the original 15 and the 25, but you also get, what's this guy? Minus a 0 offset, a 10, and you get 40. So you get the sum and the difference at the same time. That's mixing, okay? And so that's just what I wanted to show you, that it really does work if you look at it even a different way. I don't want to, yeah, let's go back to that one. Okay. So let's go to the next slide here. And so now they're going to use those and the theory to build a radio. Great. So the first thing we do is we build an oscillator, control it with a key, and then send it out. This is my version of having a string quartet stuffed in your living room, and you got a baton, and you go, there's actually a whole symphony written in Morse code. I hope you all know this. It was Beethoven. Have you ever heard of V as a symphony? It's called da. Sorry. Thank you. That's an amateur radio joke that is not appreciated by other people. Okay. If you do that, every time you go with your baton, you get a little bit of, there's a starting frequency. If you listen to the symphony, do Beethoven's Fifth, every time they go, you hear it, that's a chirp. And it turns out you have to have a chirp. Okay. The question is, how little is the chirp compared to your ability to hear and noise so that you don't detect it? Okay. And that's called a good signal. All right. So to get rid of the chirp, how do you get rid of the chirp with the string quartet in your living room? You go into the dining room and you close the door. Okay. You say, just give me concert A over there, guys. And then you open and close the door. Okay. Now you end up with less starting and stopping frequencies. And so that's what the next slide should be. What they do is they get the oscillator to go over here, and then they just control the gate to the oscillator over here. Okay. This is what the Pixie did. Okay. And that's why they have two transistors. They got one wiggling over here, and they got the power amplifier over here. It ain't much power, but at least it's working. Okay. So that's what they've got as their master oscillator power amplifier schematic. Okay, let's go on to the next one here. So now they're going to do a radio, and they're going to put a local oscillator, a mixer, and then they got their audio out. So I think the next slide is going to do what we did with the signals. You take the antenna in at 7 megahertz, put a local oscillator here at 1 kilohertz more, and you'll actually hear the guy sending Morse code from Fargo. You'll hear the for the 1 kilohertz. The very interesting part about doing this type of decoding rather than other types, regenerative and so forth, is that you can increase the power here by increasing the power of the local oscillator. That's not a free trip because you got noise and all the other stuff coming in, but you can get a little bit of a boost that way, which is kind of value. Okay, next slide. Now onto the Pixie. Excellent, finally. So this is the circuit of this guy that we just saw here. Okay, you got one transistor here doing a Colpitts oscillator, and you got another transistor here doing double duty. And this is the interesting part. Okay, this was certainly not original. This had a long history going back to 1982. I actually looked up those references, and sure enough, guys like you have been tinkering with this thing for a long time. The magic part here is that resistor right there. And if I can bother you to go to the other presentation and go down one to that guy right there. This is the transfer characteristics of a 2N3904, which is either the transistor they're using or the type of transistor they're using. Okay. they were using a 10K resistor in the emitter, okay? So a guy like me who only knows how to build very simple things, that's dumb, okay? Why is that dumb? Well, to me, 9 volts is 10 volts. 10K means you've got 1 milliamp going through. That's the maximum you can get through short the darn transistor out, you know, connect the emitter to the collector, and you're going to have 1 milliamp. Where does that put you on this curve? Way down there, okay? I mean, why have a transistor if you're going to operate down there? That's the whole point. They turn off the transistor, they turn it into a diode, and they use it as a detector for input. And so let's go back to the presentation. That's the secret of this whole unit, and I think it's really clever. I mean, this is like this is close to not using transistors. This is close to abusing transistors, but it works. So God bless them. Okay, let's go on. And this presentation, I think, does a really good job. Let's go to the next slide. Is that
That's
the next slide?
Magic Bus. Yeah, that was the next one.
I'm sorry.
Magic Bus. That was the chief.
Oh, this is the next slide. Oh, very good. Thank you. I can't hear and I can't see. Very good. So this guy calls this the magic bus right here. And your key is connected right to there. So remember, the key opens the door to the living room, doesn't actually control the baton. That's the string quartet, okay? And this guy goes to the door to the other room, okay? So this guy right here is operating at 7.5 volts. There's a technical term for that in electronics. It's called dumb, all right? Why? You're up at 9 volts here. I mean, what's going on here, guys? So you've lost the whole dynamic range of so it's not a transistor anymore. A transistor, an NPN transistor is supposed to be N, P, and more P, right? And that gets the electrons going across the base up to the collector. Well, when you pull, I actually measured this, and when you take the oscillator in here and go to the base of this guy right here, you're actually pulling north of the whatever voltage you're driving this with. So now you don't have an NP and more P, you have an NP, and this guy base is actually higher than the collector. So what you have is 2 diodes. Okay, you got 2 diodes, and what's going to happen? This guy's going to conduct this way, this guy's going to conduct this way, and your transfer characteristics are all fouled up. Well, that's the whole point of a mixer. You want to be nonlinear so that you can get all these other frequencies in there, and then they start creating the thumbs and the minuses and all this other stuff. So this is the magic bus, and every time you hit the key, you lower that and you raise it back up again. Let's go to the next one. Okay, key closed. You basically can. He's showing you the. I should have mentioned this. This is the audio amplifier. So if you go back and compare it to the Japanese 6 transistor radio, 3 of those transistors in the Japanese transistors were all audio amplifiers. Push-pull 2 in the back and a preamplifier, and so 3 of them out. Okay, so but he's still getting a pretty good response for the other 3. So the way they cheated was they just used the common operational amplifier configured as a audio amplifier for the output. Okay, and so this whole guy right here, we'll show you in a second. This draws about 4 kilo ohms as an equivalent resistance. So he's going to drop the voltage on this point right here. This diode right here, if you flatten that guy over there, he's going to go that way and short out the entire power. So you need this 1K resistor right here, because every time you key your transmitter, you're sorting out the, you got to drop the currents or something. So this guy goes away, and all you're left with is a grounded emitter at that point. Now you've got a pretty classic, what they call Class C amplifier here, because it's not because you're not going the full swing. Only when you're going portion of the way do you turn the transistor on. So let's go to the next slide. I think he actually, yeah. These guys did a really good job. Maybe we should send the reference to this thing around, because if you're really interested, I think we should.
I can forward it to the club.
So what they do here, you can see the oscillator coming off with it, and I think it's about 2 volts that the oscillator is coming out with through the capacitor, which at this frequency is like a dead short. And he gets over here and he either goes positive or he turns this transistor on. I'm forgetting about 0.7 volts. And if he goes negative, he turns that transistor off. What does that transistor have to do for a living? Well, he has to do 2 things. What he's trying to do is just run a spark coil into your automobile. You know, what do? He knows. He works on it. So what you want to do is you want to take a coil up here, you want to hog current down here. You want to create a current going through this coil, which will slowly build up. Now you release it, and what happens? It reverses voltage, and you get this nice spark. You can do lots of things with that, like build Tesla coils a couple of times. Okay, so to do that, he's got a problem. This guy right here has got charge on him. So now he's got to get rid of the charge on that capacitor in order to do that. So he's fighting those 2 problems both, and that gives him a resonance, and he's driving a voltage out here that's pretty good. I mean, he gets about a 4 or 5 volt swing out of one transistor. So you're not going to reach Italy on this, okay? But you know, you might reach Fargo from Detroit Lakes, okay? But at least it's a place to start, okay? So anyway, that's what happens when he closes it. It's a pretty classic transmitter. Am I running over time?
No, you're good.
Okay. So the next part is where it's interesting. Okay. So this is the receiver, is where these guys are off the mat, as far as I'm concerned. I mean, I would have eventually, you know, given 100 years, come up with the transmitter side. I'm not coming up with this side. This is beyond my ability. So, okay. He's got his oscillator coming in here, as he did before. But now when he opens that key, he's running through that magic bus in the 10K. When he does that, this guy is now higher voltage than this one, so that diode turns off. This guy powers the audio amplifier. And that big guy right there just takes all the audio over there. You got enough filters in there that you've actually filtered out all of the RF. Where's the antenna? Where's the input? You know, well, he's using the same antenna that he had out. I mean, a perfectly good pi filter there. All of this, the first Pixie was tuned to the 80 meter band. The one that they're still now is tuned to the 40 meter band. So you'll see these capacitors and resistors change. If you compute the I omega L's and the 1 over I omega C's, they all end up being 50 ohms, and you're getting a roughly 50 ohm transmission line out the end. What? I lost track of what I was saying.
Antenna.
Sorry. Okay. Anyway, if you've got this nice filter out, it's the same filter as coming back in. So if you got the thing coming back in, why don't you use it? So how are you going to use it? You're going to use this guy as a diode by taking that base and jacking him up. Okay. And when you do that, he's no longer a transistor, it's 2 diodes. Sounds good. So now you're going to mix that with this guy coming in, and the combined mess is going to give you 4 frequencies, right? It's going to give you the, as they said, 71, 7 plus 1 kilohertz, 7 megahertz, the difference and the sum. Well, you put enough inductance in there to kill all the high frequencies, and the only thing you're left with is the small difference in frequency between you and the signal coming in. Okay. That is essentially how that resistor works, receiver works. Let's go on to the next one. Okay, and now he gives you a little bit more details. This guy goes to 7.75. He's talking about the high resistance there, and he's talking about the fact that he's killing all of the RF through the capacitor. Okay, let's go to the next one. Now, there's been a few changes over the years, okay? This little guy right here has a knob on him right here. And when you plug them in and you're listening to a lot of people use this thing, by the way, because they're all lined up on that frequency. You can turn this and you, how's he doing that? Okay, well, he's making a variable capacitor down here that you can get about 2 kilohertz off of a crystal oscillator. You can push him one way or the other. So he puts a diode in there and reverse biases it, so you've got the PN junction, and the more voltage you put on it, it floats back and forth, and you can change the capacitance in there. So he cranks the voltage right through here. This crystal couldn't care less about the voltage. It's got a bunch of capacitors in there anyway. It didn't care about the DC voltage. So you can do whatever you want to there. So that works really nicely. It just uses a 1N4001. I mean, just standard old, you can go get a varactor, but you can also just use a diode. And it's just like, why not? Okay, next slide. Then they stuck a little light in here, an LED, and a little buzzer in there, which actually is kind of nice because you sit there and you're transmitting away and you don't know what the heck's going on the other side. So it's nice to get a little bit of feedback. So, but if you're a purist, like you don't want to, or you're running off a 9-volt battery, you can pull this jumper out and it'll disconnect the buzzer, which is one of the major current draws from this thing when it's not transmitting. Okay, that's side tone and the blinky light. And then he did the next slide. He talks a little bit about these guys came with negative or positive, and you never knew what you were going to get, and so forth. So what they did was they just put a full wave bridge over here. Since a full wave bridge can go either way, hey, it works for DC as well. It works as AC. So the problem is you pay for it by 2 diode drops. You got to go through one and you got to go through the other. So you thought you were having 9 volts, well, you're going to end up with 6.6 or something. You kind of, I'll talk about in a minute. How do you increase the power on this? And the first thing you do is cut that guy out. Okay. I think that's about, that's it. Then that's it. That's the final Pixie schematic. And they added a little bit of stability here and a little bit of stability here. And the next slide is the, this is that schematic, the one from the Chinese. And I mean, you can say a lot about the Chinese. I love them. I mean, they do good work, straight, get the same thing. You don't get anything else. You may not get the documentation. If you do, it may be in Chinese, but the stuff does work. So that's pretty good.
Thank goodness we have Google Translate.
I'd like to flip briefly to my presentation if I could. Okay, so what I did was I modeled this thing. And pick your favorite spice package. I like to work in LT Spice just because I'm kind of used to it. Problem with LT Spice is they've got all the parts in the world that analog manufactures. And they got none of the parts that no analog does manufacture. So you got to kind of stick in your own spice models every now and then. There are about a dozen spice models for a QM3904 on the web. None of them agree with each other, and none of the spice models agree with the spec sheets. I know because I've tried every one of them. So it's a stochastic situation, and you take your pick. So I took my pick. What I did was, without going into it in great detail, I modeled the oscillator and the transformer, the amplifier section in the input mode. And I put in a signal that was 10 kilohertz different. This is the base right here, the yellow one that's going into the audio amplifier. And if you look really hard here, you can see, point or something. You can see, yeah, there we go, right there. You can see it go down there and up there, down there and up there at 10 kilohertz apart. And that's amplitude modulation. This is not amplitude modulation here, where it goes both down and both up. That is what you do not want when you're trying to mix. That's exactly what you want when you're trying to go linear. So at least, I mean, now, the fact that Spice can model it doesn't mean it's right. It's just a different way of looking at things. If I could go to the two down, we already did that one. This one. Yeah. So now, very briefly, how do you get some power out of this guy? Well, you go get a linear amplifier and plug it in. Okay. But aside from that, there are a couple of ways you do this. One is the final transistor is basically limited by how much it can pull down. Okay. If it could pull down more current, that coil would have a bigger magnetic field. And then when it collapsed, you get a higher voltage, and it would kind of, if you remember the old 53 Chevys and the spark plug went together and you had to have a capacitor across the spark plug, your antenna is acting like the spark plug, the capacitor against the coil. That's where the energy is going. Well, to do that, you got to pull down hard on the transistor. So what they do is what any good ham would do. Takes two transistors and solders them together and puts them in there. What happens when you do that? They get hot. Oh, so you got to put a heat sink on them, and et cetera, et cetera. So they go from about a quarter watt to half watt, which is what you basically get out of one of these. They can get it up to 2 watts, okay, which for QRP guys is, progress. To do that, go back to the string quartet in your living room. You're now pulling and you're getting that chirp on both sides because you're getting more and more energy going through this. So the other addition that they recommend when you're amplifying it is to put a little more capacitance across the first as you go out the antenna over here. Okay. You add another capacitor here. The other way of looking at that is that your inductor is creating a reactance that's very, if you look on a Smith chart, it's up there. You're trying to get it down to the real part down here to match the impedance of the transistor. So what you're doing is adding capacitance to balance the inductor so that you're getting a real impedance to go out. That's another way of looking at it. It gets you to the same thing. So before I leave this one, what does a dumb guy like me do? And boy, am I dumb. Because what I do is I do things that I think are reasonable and they all fall apart, like breaking my Pixie. So I think, well, I want to tune this thing. I don't want no crystal there. I want to be able to tune it, lots of ways. How do you do that? Well, you've got an inductor and you've got a capacitor. So this old boy down here is 30 millihenries. Why don't I put an inductor over there? Well, I open my cheap Chinese filters here, chokes. I don't see no 30 millihenries. I see a 30 microhenry. Oh, what's 1,000 among friends? So I put a 30 microhenry in there. But now if I change the frequency of that guy, I got to go change, remember, 1 over 2 pi square root of LC. Well, down L, you better up C. So I go from 1.0156 picofarad to 0.0156 to 15.6 picofarad. So I go, okay, now I'm back in business, right? So actually, that works. I actually get a frequency, and you can see it. I go down a little bit here. Notice the exquisite construction on this fine prototype board. You can see I'm resonating at 7.08 megahertz. There's a megahertz on there. I got one of these cheap radios that had a capacitor and I could barely turn, so I had to put some torque on it. So this is my knob up here. Okay. So I'm tuning this thing, and my problem is I don't hear very well. Okay, so I got this connected to my inverted V out there, and I'm listening to this thing, and I can barely. Well, my son's going to come here next month, and he's used to be a musician, and he's got, I don't know, he got all the hearing genes, so he's going to. I'm going to ask him to hear it. So, but the question is why it did not work as well as the real one. The question is why. Well, let's go back up here. I changed the L by a factor of 1,000, and I changed the C by a factor of 1,000. Well, 1 over 2 pi square root of LC, those cancel. But what doesn't cancel is square root of L over C, which is the reactance of this guy, okay? So what I did, if you divide those and get them out, I actually made the Q, or the reactance of this thing, worse by a factor of 1,000, which means my resistance, physical resistance, over the, went way down. So if you look at this breadth of this, I shrunk it away. So basically, I did everything you're not supposed to do, okay? So I think it was an interesting exercise. I learned a lot. And I think the right thing to do is just take this and run it into a linear and go from there, and you might get yourself about 15. That's my experience with Pixie. Thank you all very much.